Hi, I'm here to do the calculations. Just one example. You have trial 1, trial 2, trial 3 to do, but I'm just going to do trial 1. I'd like to do trial 2 and trial 3 for you, but you know what? I didn't save my lab notes properly, so I don't have the temperature for my trial 3, and I also forgot to take the mass of the calorimeter at the end of trial 2 and trial 3. And the only mass that I have for the calorimeter being full of stuff is for trial 1 right there. So make sure that you get the mass and the temperatures at the end of each of your trials, and make sure you save that before you exit the lab by pressing the Save Notes button. I just forgot to do that. So silly. But I could still show you how to do the calculations using this trial 1 here. So the mass of the empty calorimeter, it's a bit obvious there. It's just straight off of my notes right there. The initial temperature of the calorimeter and the maximum temperature of the calorimeter, and the difference, and the mass of the calorimeter and its contents. Don't forget to use these units, that's important. The mass of the contents of the calorimeter by subtraction. Sorry about that. Wow, this is kind of fiddly there. Okay, so by subtraction, 194 minus 18. That's 174.413. 175.413. Okay, and that's in grams. And the moles of magnesium that reacted. Okay. The moles of magnesium that reacted is something to calculate, so I'll help you calculate that now. I used this many grams of magnesium, 0.45 grams. So that was Now, to get the moles, I need to get rid of these grams of magnesium. So I know that there are 24.305 grams of magnesium right here, 24.305 grams in 1 mole of magnesium. So if I do that on the calculator, I get 0.01851 moles of magnesium. Now remember, it's important to keep track of the significant figures, but because this is an introductory course and it is for most of you will be nurses or something similar, clinical rather than research. I'm going to let you use whatever number of significant figures you prefer. May I recommend something at least 3? It will help you to get accurate calculations later if you use this same number later. So this, I'm putting the number of moles. All right, now that was for trial 1. Now I'm going to skip trial 2 and trial 3 because I forgot to get the masses after the chemical reactions. And now I'm going to calculate the Q. So now remember, the Q is, here, let me write that equation again for you. Oops. Okay. Just get another one. Okay. Now remember that the Q of the reaction is equal to the Q of the water, except for the sign, because in the reaction heat is lost and the water heat is gained. And the Q of the water, remember, equals the mass of that water times the specific heat capacity of that water times the change in temperature of that water. So what was the mass of that water? Now, the 1 molar hydrochloric acid was mostly water because this is a solution of 1 mole of HCl in 1 liter of water. 1 liter of water contains 55 moles of water molecules. That's just something that's standard for a given temperature. So at room temperature, 1 mole of water contains 55 moles of water molecules. And this is a little lower than room temperature, so that will be even more moles of water molecules. So what I'm trying to say is that this solution is mostly water. So that means the mass that I took here, 194.013, except for the magnesium, which was 0.45 grams, is mostly water. So to get the mass of the water, to get just the mass of the water, I'm going to do 194.013 grams, which was the mass of the whole calorimeter, minus the mass of the calorimeter, 18.600 grams, minus the mass of the magnesium. I could also have just taken this number, 175.413 grams, and subtracted 0.45 grams, the mass of the magnesium, because in this number, the calorimeter is already subtracted. So I get 174.963 grams. That doesn't make sense though, because this, oh yes it does, this number is lower. So 174.963 grams is the mass of the water. Now, we can get even more precise here by subtracting from here the mass of the hydrochloric acid. Since we used 1 mole of hydrochloric acid per liter, and there were this many liters, I can calculate the moles of hydrochloric acid, and then calculate the grams of hydrochloric acid. Then I can subtract that from the water here. But I won't require you to do that. I'll just have you use the mass of the water as an approximation, and we'll calculate the heat of the water from there. So, time to do that. Okay, now the Q of the water is equal to the mass of the water, which was 174.963 grams for me, times the C of the water, which is 4.184 joules per gram per degree Celsius for anybody, times the change in temperature, which was 11.5 degrees Celsius for me. Notice this is 3 significant figures, so my answer is going to be in 3 significant figures. $8,420. That's 8,420 joules. This got absorbed by the water. So that means that the Q of the reaction is 8,420 joules, and that means that the negative Q of the reaction is 8,420 joules. That means negative 8,420 joules is the Q of the reaction, which means 8,420 joules got released by this chemical reaction. So now that I know that, Q of the reaction, negative 8,420 joules. And now I need to find the molar heat of the reaction. So the molar heat of the reaction is going to be this number divided by the moles of magnesium that I used. And those number of moles are right here, 0.01851 for me. It'll be something different for you. So I take that number of joules from the chemical reaction divided by 0.01851, and I get this large number, this 454,809. So you can use the number of significant figures that you prefer for this particular class, but I'm going to do this right. Let's see. It was 8,420. Here, let me just show you what I'm doing here. So it was 8,420 divided by 0.01851 moles. So this was joules. So this is actually negative. So now this is the molar enthalpy of the reaction. That is the enthalpy of the reaction in 1 mole. So when I divide this, I will get it for 1 mole. Units will be joules over moles, as you see here, joules over moles. And this is 3 significant figures. So the answer should also be in 3 significant figures. The answer, the answer was 454, but this should be rounded up to 455 because that number after the 4 is more than 5. So it's 455,000. So 455,000. Where is? Oh, here it is. So it should be yes, here it is. So it should be negative 455,000 joules per mole. Now, because this is a large number, it's convenient to convert this to kilojoules. There are 1,000 joules in a kilojoule. So if I have negative 455,000, then in kilojoules, that'll just be negative 455 kilojoules. Because remember, there are 1,000 joules in a kilojoule. So kilojoule is a larger chunk. So if I have 455 thousandths, then I must have 455 kilojoules. Okay. Now that's my answer there. So negative 455 kilojoules per mole. Now it is necessary to type kilojoules per mole here, and it is also necessary to have the negative sign there. If you don't have the negative sign, then you imply to whoever is reading your paper, namely me, that the chemical reaction absorbed this much heat. In other words, the water turned colder, which is not what happened. In number 6, you want to calculate the average of your 3 trials. So add them up and divide by 3. These will all be negative numbers, and so when you add them up, you will get a large negative number, and then you divide by 3, you'll get a negative number that is similar to this one that I have, something like negative 400 or negative 500 kilojoules per mole. Okay? Now, there are some approximations that I've used here that you don't need to use if you prefer to be precise. In your lab, I'll show you where in your lab I'm talking about. In your lab, there is this information in the background tab of your lab manual, and it shows you how to be more precise or more accurate also. So if you want to be more accurate, and I don't require this, but if you want to be more accurate, you can include the heat that got lost to the styrofoam cup. So remember, in your lab we're using the styrofoam cup, and I have assumed in all of my calculations that all of the heat goes to the water. But in fact, some of that heat does get into the styrofoam material, and the styrofoam material gets a little bit warmer, as you have experienced when you hold a coffee. On a cold day, if the styrofoam is a certain temperature, maybe kind of a low temperature, and you hold that in your hand, you pour coffee in it, the styrofoam does heat up a little bit, and you could feel it getting warm. It won't be hot, it won't be anywhere near as hot as the coffee, of course, but it'll be a little warmer than the cup that is empty. So how do you account for that loss of heat? Let me just draw a picture to show what I'm talking about. Cup, chemical reaction, water, styrofoam. So no heat or hardly any heat leaves to the air outside, but there is some heat that goes into raising the temperature of the styrofoam material right there, just right in there, you know? So, the lab manual is telling you that the amount of heat is this. The change in temperature times a constant. So this is the heat capacity, not the specific heat capacity, but just the total heat capacity of the calorimeter, of the coffee cups. So you can use that. So you know that the Q of the water equals M of the water, C of the water, times delta T of the water. Now, if you added to that the Q of the calorimeter, it could make your result more accurate. Now I say could, and I'll explain that in a moment. So that would be the Q total. So, all right, this is actually. Let me rewrite that. Sorry about that. Okay, so let me start with the Q of the reaction. So the Q of the reaction should equal the Q of the water plus the Q of the calorimeter, because if you assume that the heat is not just getting absorbed by the water, but it is also getting absorbed by the styrofoam material of the coffee cup, then the Q of the reaction, or the negative Q of the reaction, the heat that gets lost by the reaction, is getting absorbed by the water and the calorimeter. Okay, so if you assume that, then you've got, for the water, the mass of the water, C for the water, delta T for the water, and then for the calorimeter, the heat capacity of the calorimeter times the delta T of the calorimeter. Okay, now here, we don't use the mass. Why? Because this is not the specific heat capacity of the calorimeter that's given to us. What's given to us is the total heat capacity, or the calorimeter constant. So that's the amount of energy it takes to raise the cup, the styrofoam material itself, up 1 degree Celsius. The difference is that when you take the specific heat capacity, such as when we take the specific heat capacity of water, 4.184 joules per gram per degree Celsius, it's that grams. This is the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. But we're not using grams here. We're just using joules per degree Celsius. So it's the amount of energy it takes to raise the whole cup, the empty cup, by 1 degree Celsius. So this is joules per degree Celsius, and this delta T, this is of course still degree Celsius, they'll cancel to make joules. Everything in here will also cancel to make joules. Joules plus joules, you'll get an energy. So that's how you'll do this. They give you in the background material the number 9.3 joules per degree Celsius. You see that there. Okay, now, why do I not require you to do this? You can do this if you like, but I don't require this because there is an inaccuracy inherent in doing this, and it's pretty severe. The inaccuracy is right here. We never measured the temperature of the coffee cup, and we don't have any guarantee, because of the nature of the styrofoam material, that the temperature of the coffee cup is going to be the same as the temperature of the water. The water started at 21.5 degrees Celsius, and the coffee cup started at 21.5 degrees Celsius. That we know because we measured it like this, 21.5 degrees Celsius. However, we never measured the styrofoam material itself after the chemical reaction. We just measured the total temperature inside here after the chemical reaction. Now, why would it ever be different though? Why can't we assume safely that the temperature of the coffee cup styrofoam material would be the same? So for me, it was 33.0 degrees Celsius after the chemical reaction. Why can't I say that the coffee cup is also 33.0 degrees Celsius after the chemical reaction? It's because it's not. If you put 90 degrees Celsius coffee in your coffee cup, is the temperature of the water in here 90 degrees Celsius? Yes, it is. when you hold the coffee cup with your hand, is the temperature of that coffee cup 90 degrees Celsius? No, it's not. Because if it were, you would sue the styrofoam company. The design of the coffee cup is meant to make sure that the temperature on the outside of this material is never the same as the temperature of the inside, as long as there is a large temperature difference. So anyways, this is why I don't require you to do the calorimeter constant calculation that appears in the lab manual. So if you do it, it's fine. I'll still give you full credit. If you don't do it, if you just use the Q equals MCAT for the water, as I have done, that's fine. You'll get full credit. Let me know if you have any questions. Thanks very much.